Hello, this is my first ever attempt at a YouTube video, so hopefully it'll turn out okay. I thought somebody out there might be interested. In fact, a friend of mine convinced me that people might be interested in this topic. I set out to write a 6502 emulator in C under Linux, and I thought I'd share with you my learning processes, my learning curve, things that I had to sort of work out along the way, mistakes that I made. So the series of videos really is one of those kind of, this is where I started, this is the next step I took, this is the step after that I took. I uploaded most of this stuff onto GitHub in various forms, sort of labels, sort of first, second, third, fourth, and so on. And each is an incremental step from the previous step. So it's kind of started off with trying to emulate the actual bare bones of the 6502 instruction set, and then work my way sort of forward to try and make this much easier to do than jumping in and doing a whole thing in one big go. Anyway, the 6502 is an 8-bit processor. There's tons and tons of resources out there on the internet. I'll try and link in some of them as we go. Some really interesting YouTube videos as well, but there's plenty of stuff on the standard web. The 6502 is what's called a memory mapped processor, and we'll come on to that in a second. So I drew this out for myself on paper, but I thought I'd put it on electronic format. It might make it easier. Each one of these little boxes represents 8 bits or 1 byte, and the only register that is 2 bytes is the program counter, and 2 bytes equals 16 bits, and therefore the maximum amount of memory that a 6502 processor can reference is 65536 bytes, or 0 to 65535. And down the right hand side here, we kind of split it up because the way the 6502 does it is in pages. So you've got something called the 0 page, and then so that runs from 00, in fact it's 0000, through to 00FF, as we can see there. And then page 1 is there from 100, or in real terms it's 0100, through to 01FF. And just to make it kind of logically obvious, you've kind of got page 4 there, which starts with 04 and runs through to 04FF. And then you got like page 10, and then the final bit down here. So we start off with the registers. The 6502 has 3 of them, really, 3 main registers that you can use anyway. The A, X, and Y. Then it's got the stack pointer. Then it's got the status register and program counter we've already discussed. So the status register is an interesting one, in the fact that if you for those of you who don't know binary, again, there's loads of resources on the internet. I'm not going to bore you with the details of that, but this is a binary number. So 1, 2, 4, 8, 16, 32, 64, 128. So that bit there, the one with the underline on it, that's 32. So what is it? Bit 5, 1, 2, 3, 4, 5. No, it isn't. It's bit 6. And that there is always a 1 according to the 6502 documentation. So in our emulator, although that's sort of signifies an underline there, we will always set it to bit 1. So 32 will be the number that it will be set to, if everything else is a 0. Page 1 is a stack, the CPU stack. So that's what the central processor uses. There's a lot of resources out there on the internet. Some of it is wrong. The 6502 sets the stack pointer FF by default. We'll go to stack pointer in a little while, and counts backwards. So it doesn't start at 100 and work forwards. It starts at FF and works backwards. The rest of the memory is available for us to do with pretty much what we want, with exception of this top bits here. And these top bits here are the non-maskable interrupt vector the reset vector and the IRQ vector. And a vector is just a pointer. It's just something that says, I'm just holding the memory location that I really want you to go and look at. So inside of those three locations, the memory locations of where the code starts. Talking of code, the 6502, with it being 8-bit, each of these locations is 8-bit, so that means it can only store 00 through to FF or 0 to 255 in decimal. That poses as a slight interesting issue, is how do you reference a memory address in an 8-bit byte? And the answer is you use two of them. So in reality, what you end up doing is you would end up putting 1 bit in here and 1 bit in here, or whatever. And the 6502 is little endian. So what that basically means is that the low byte goes in there and the high byte goes in there. So if we wanted to reference, for example, the memory address 400, then 00, oops, I'm not very good with this application either. Then 00 will go in there, oops, and 40 will go in there. In fact, 04 would go in there. Now, it's not actually memory address 400, is it? It's memory address hex 0400. And we'll try and keep it in hex all the way through these videos. So I'll try not to say 400 and 100 and 200 because that's not actually accurate. So with it being little endian, what that basically means is that the low order byte goes there, the high order byte goes in there, and when the CPU reads it, it rearranges it. But what happens is when you see it in memory, when you see a disassemble or when you see a memory dump or whatever, you've got to kind of remember that actually this backwards. Alright, so the same thing happens here. So if we take that one there, which is a reset vector, so the first time the CPU does, it comes on and it says, I really don't like this application. I'm not very good at it. I reckon there's a user error more than the application. But anyway, so what you end up with is, let's say, for example, our code starts at C000. So the 00 will go in there, right? And the C0 will go in there. So that would tell the on a reset. So when you turn the computer on, when the CPU first starts up, it will go fetch C000. And it would put it into the program counter, all right? And the program counter is up here. So the program counter will actually hold C0, whoops, again, another user error. You get used to this, I'll get used to it anyway. C000 like that, all right? So that's basically the way that little endian works. Just to reiterate, the 6502 is a memory mapped processor. So what that basically means is that some of this memory here, down here, for example, where I've put something could be mapped here. That could be a place of a ROM, for example, so that you could put your I/O in there, or you could, it could be your keyboard buffer, or it could be your screen, or it could be your parallel port, your serial port, whatever it is, So whatever you want to map in there, and it's down to basically the designer of the computer. So you look at Commodore 64, VIC-20, BBC. Or any of them really, and they all have different memory maps, and it's just simply down to how the designer has done it. And whenever you reference that area, the 6502 is basically talking to whatever it is that you've mapped to that area. It could just be memory, it might be ROM, or anything. So that's pretty much how the memory map looks. The 0 page, keep in mind for later, because the 0 page is a special area, and it's special because 0 page is 0000 and 0001, 02, and so on. But you can reference it with just an 8-bit byte. So if you take the program counter there, right, and that's 00, so if the page counter and the program counter is 0, right, and this is your actual memory counter inside of the page counter, Again, I really don't like this application, but that's down to me, I reckon, rather than the app. So that there, if that becomes 0, 1, right, I'll get this right at some point today, oh, for the love of heaven. Oh well, never mind about that. But if whatever you put in there, okay, there we go. So if that becomes 0, 2, for example, you can ignore that 00, and you can ignore, and that is the only one that matters. So that 8-bit value in there is the only one that matters, and that's really useful later on, because the more bytes you've got, the longer it takes the CPU to process them. So 0-page instructions are faster. Now, we'll bear that in mind for later on, because whenever you're doing calculations and things like that, the 0-page instructions, are the ones to use. That's why when you find things like BASIC or any of the kernel routines or anything like that on any of these machines, on the old 8-bit machines, most of the stuff that they try and reference is in 0-page, because it's quicker. The other thing to notice is that the 3 registers here, the A, X, and Y register, the A stands for accumulator, and the X and Y register are types of index registers, which we'll talk about in a little later on. But the A register is the one that you do most of your maths on, so that's the one that is used for addition, subtraction, stuff like that. The 6502 doesn't have any multiplication instructions, with the exception of multiplying and dividing by 2, because multiplying and divided by 2 is left and right shift. But in actual terms of multiply, you have to write your own routines to do that, and that's kind of one of the quirks of the old 8-bit machines, the limitations that they had. For our purposes, well, for my purposes, for the emulator, what I did, and I kind of ignored timings to some extent, but I did try and implement all of the addressing modes. I tried to implement all the various modes, 0-page and things like that. The main difference is that I didn't actually care much how fast it did it and whether it was time inaccurate and things like that. I was more interested in the fact that it actually worked for the first side of it, and that I could get the instructions to decode and stuff like that. Okay, that's pretty much it for this first video. We'll move on to the next video and we'll talk about the actual stack within the 6502.